I was thinking about that. I thought about that, but instead of just having to switch it over, might be not. I thought it was really Are you good? Are you live?
Yeah, just started live. Yeah.
Okay, perfect. So we'll start in about 2 minutes.
Okay, no worries. Hi. Good, how are you?
Good.
What's your name?
Pardon me?
What's your name?
Mark?
Mark? It's nice to meet you. Evan. I'm the new live guy.
Yeah, we met
yeah,
on Thursday.
yeah, at the office, yeah. I just
But you're replacing Zach.
replacing
He doesn't have
Zach.
to travel a whole hour to get
Start
here.
him now.
Right.
So are you're a student?
Yes,
All right. Hello, everybody.
Hello.
Welcome to the Queen's Observatory. This is the July open house, and we have a treat in store for you. We have a jam-packed, science-filled, cosmos-filled event planned out for you. Today, our talk, if you looked at our promotions, is done by Ben Tam. But before we get started, I want to do just a couple announcements about the science outreach things that are going to go happen between today and the next open house sort of thing. All right, so the first thing on our agenda is Girls Camp. This is sort of a camp that physicists at Queen's University are organizing for girls in grades 7, 8, and 9. And they are sort of getting hands-on experience with leading female physicists in astronomy physics from around the world. So if you know someone who might be interested in such a camp, do tell them about this. It's free to register in the camp, just as a side note. And if you're further interested, visit the website that's listed below. Next up, astronomy on tap. This is the first time I've gotten this sort of a laugh. Perfect. So astronomy on tap combines two of my favorite things, astronomy and beer. So this is the third time Astronomy Untapped is featuring. It's going to happen on August 14th at the mansion, from the top floor of the mansion. It's called the living room, starting 7 o'clock. And this time we're going to be talking about the tools for the cosmos. Basically, this time we're going to have 3 scientists come up and chat with you about instrumentation that happens in astronomy and astroparticle physics. Basically, how do you build things to understand the foundations of the cosmos? All right, and that's it. So now we're going to turn on to our main event. Well, is there a question? Yes.
Do you have to be teenage?
No.
No, it's all ages, but most likely you won't have a beard. Yeah, I'd ask permission for your mom before giving people to you. Anywho, so back down to the main event. Today we have Ben Tam, who's giving us a talk about how to probe the origins of the universe. Ben very recently started his PhD at Queen's. He comes to us from an undergrad at McGill in Montreal. Ben is also working with Snow Lab, which I very recently had the chance to go to, and he gave me a private tour to the experiment that he's going to talk about today. Apart from the science that Ben is involved in, Ben is also an avid public outreach person. So a part of the open house is actually to take you to McDonald Institute Visitor Center, for which Ben is the head public outreach person. And finally, Ben also, apart from that, is also very interested in teaching and giving lectures. Ben very recently got the 3rd prize in the young person's lecture competition, and also has received multiple different awards for teaching at Queen's. So without further ado, I'll welcome Ben.
Well, thank you for the lovely introduction, Nick. Is this working all right?
Yes.
Are you guys going to be back? Okay. So thank you very much for coming out. Today, I'll be talking to you about how my team and I are combining physics, chemistry, and engineering in an effort to understand one of the most basic of all human questions: how do we come to be? Now, in order to understand this question, which is really a matter of the origin of the universe and everything within it, such as you and I, we first have to understand what it is that actually makes up the universe. So it turns out about 2/3 of the universe is what we call dark energy. It's a mysterious field, responsible entirely for the expansion of the universe. About 1/4 is dark matter. We can't see it, but we can feel its gravitational effect. It flows through us, penetrates us, and binds the galaxy together. Finally, not but 5% of the universe is what we call ordinary matter, and this is what makes up you and I. But not just you and I. Everything you've ever seen, or smelled, or touched, everything from the smallest life forms to the greatest stars, is just 5% of the universe. But what I believe is the 5 most important, because it's where we live in. Now, what exactly makes up this 5% is ordinary matter? You're probably familiar with this, the periodic table of the elements. Some people call it the building blocks of matter. But you're probably aware of the fact that these aren't fundamental building blocks of nature itself. They're made up of smaller particles. The proton, the neutron, and the electron, what we call the beta particle. Turns out, while the electron is a fundamental particle of nature, the proton and neutron are not. They're made of smaller particles, yet, called the up and the down. And these are the 3 particles which make up the elements. They're joined by a 4th particle, the neutrino. They're very hard to detect, but their existence is essential for the framework of the universe. That's not all though. For each of these 4 fundamental particles, there are 3 classes, or generations, each heavier and less stable than the last. And these are the 12 particles which make up ordinary matter. Collectively, we call them the fermions, because their behaviors obey the Fermi-Dirac distribution. And there are an intimidating number of them, but they're all named for arbitrary purposes and historical reasons. So for all we care, they can be named after different sorts of dogs. You can tell the different dogs apart because they each have unique quantum properties, and these quantum properties are dictated by the Dirac equation. And to recover the quantum properties of a certain dog, you solve the Dirac equation for the particle's quantum wave function. And now when you do this, it turns out that each dog has two solutions, which means that for every dog particle, there's an equal but opposite anti-dog particle, the same in every way, but with an opposite electric charge. And of course, an anti-dog particle would just be a cat particle. Now, dogs and cats, they have to exist in perfect harmony, as we know. So whenever you create a dog particle, you must also create a cat particle. And when a dog and a cat come together, they destroy each other. This fundamental symmetry is the most basic framework upon which all of our knowledge of science is based upon. You may have heard it said as the law of conservation of matter. And every rudimentary science class begins with this simple postulate: that matter cannot be created or destroyed. But a more accurate way of saying this is net fermionic matter cannot be created or destroyed. You can create a dog, but you must also simultaneously create a cat. And you can destroy a dog, but only if you also destroy a cat. This perfect balance is bedrock upon which all of our understanding of all of science rests upon. Now, the 12 dogs and 12 cats and how they interact with each other within the paradigm of the law of conservation of matter is written in a set of rules that we call the standard models of particle physics. And since it was first postulated about 50 years ago, it's been proven right time and time again. And that's led many people to say this statement, that the standard model is the most complete, well-tested, and well-understood framework in all of science. So if you choose to believe this generally unattributed quote, then very good job. Pat ourselves about that. We now understand 5% of the universe, but the 5% that I think is most important. So we close the book of particle physics, we all don't know, and we all recognize that they think those things. But hang on, wait a minute. If dogs and cats are created in equal proportions in every scenario, that must also include the origin event of the universe, the Big Bang. And in the early, tight confines of the early universe, all the dogs and all the cats should have interacted with each other very quickly, and the universe should have ended as quickly as it began. And how can this be? You and I exist. And more than that, you and I are made of dog matter, not cat matter. And in fact, almost everything's made of dog particles. Where did all the cat particles go? When it comes to the law of conservation of matter, and therefore all of science, are we barking up the wrong tree? Before we turn tail on the standard model, though, nature has thrown us a bone. There's one particle, the Garfield, a cat, and its counterpart, Odie, a dog. And these particles are special in that they're the only particles with a combination of these properties. They have mass, but no electric charge. And because of this unique combination, they may not just follow the Dirac equation, but a slight modification called the Majorana equation. Now, if the Odie, what this means is that the Majorana equation only has one solution, which means that if the Garfield and the Odie are Majorana particles, not Dirac particles, they may actually be two different ways of looking at the same particle. Now, why is this important? You may be aware of something called radioactive decay. And that's when one nucleus changes from one type to another while releasing excess energy in the form of new particles. One such radioactive decay looks like this. Again, you have a nucleus changing from one type to another while releasing excess energy in the form of two Snoopies and two Garfields, two dogs, two cats, preserving the balance as always. And this is what we call double Snoopy decay. But if the Garfield is a Majorana particle and therefore the same as the Odie, very occasionally during double Snoopy decay, the two Garfield-Odie combo particles will see each other within the nucleus and destroy each other. And you only get the two Snoopy particles come out. This is what we call Garfieldless double Snoopy decay. But look at this. You get two dogs and no cats. And this is enough to let the dogs out and dominate the universe that, like you've seen, they have done. It is, as they say, a dog-eat-dog world. Now, the sleeping particle is more commonly known as the electron or the beta. And the Garfield and anti-Garfield is more commonly known as the antineutrino or neutrino. If they're the same particle, we just call it neutrino, of course. So instead of Garfieldless double snoopy decay, we call this neutrinoless double beta decay. Now, how do we go about seeing neutrinoless double beta decay? Well, we take advantage of a special property of all radioactive decay, and we call that property the Q value. What this Q value is the sum of the energies of all of the new particles that were created. And for a given radioactive decay, the Q value is the same every single time. So, when we take regular double beta decay with two Snoopys or electrons and two Garfields or antineutrinos, we can measure the energy of the particle and see what comes out of the Q value. Now, the antineutrinos are very challenging to detect, but we're very good at determining the energy of electrons. We do that by converting the energy into light and seeing the intensity of that light. So we do this many times. We measure the two energies of the two electrons many times, and we create a histogram, what we call an energy distribution. And it looks a little like this. Here on the x-axis is the energy of the two electrons carry away some energy of their own. But in the neutrinoless case, only the two electrons are created. So in every single time, they must have exactly the energy of the Q value. So if we look at double beta decay and we see a peak here, a distinctive peak here at the Q value, we know beyond a shadow of a doubt that neutrinoless double beta decay does exist, and that this is the solution to the origin problem of the universe, a solution that we call leptogenesis. Now, the best way to find neutrinoless double beta decay is in the element tellurium, because of all of the very few elements that can undergo double beta decay. Tellurium is the most abundant in the natural world. But we have a few problems. First, the average amount of time for tellurium atom to undergo double beta decay, or its half-life, is 10 billion times the age of the universe. So in order to have enough double beta decays to build our energy distribution, we would need trillions upon trillions of atoms corresponding to dozens of tons of tellurium. And this here is the energy distribution if neutrinoless double beta decay does exist. And you can see it looks exactly the same as if it didn't exist. And that's because even if it does exist, which it may not, neutrinoless double beta decay would be more than 1,000 times more rare than the regular double beta decay variety. So in order to see it, we have to zoom into this little area here, let's blow this up. And this is all you get. This is everything you get if you're trying to look for neutrinoless double beta decay. So in order to see neutrinoless double beta decay, you would need a device that can not only house dozens of tons of tellurium, but have an energy precision and resolution unlike anything the world has ever seen before. And the dream of such a detector materializing as this, what we call the Snow Plus experiment. This sphere here is the main body of the Snow Plus experiment. It's 5 stories tall. Within it, we're going to place 100 tons of tellurium within 1,000 tons of a special chemical compound that will take the light from the electrons and magnify it over 1,000 times in order to see every last detail in the energy distribution. We're surrounded by 10,000 of these dots. Each one of these dots is an ultra-sensitive camera. So good, you can see the light from a candle if it was as far away as the moon. The Snow Plus experiment is named such because the successor to the submarine neutrino observatory, or SNO experiment. The SNO experiment most famously won the 2015 Nobel Prize for discovering that neutrinos could in fact have mass and could be made around particles in the first place. But the SNO experiment wasn't nearly good enough to see neutrinoless double beta decay. So we had to make upgrades or improvements in every facet of the experiment, from the supporting hardware, the calibration tools on the outside, to the camera systems and the vessel on the inside. To deal with the greater amount of data because of our chemical compound, which creates more light, we've had to completely redevelop leading-edge electronic systems and data readout systems. And our chemical compound itself requires precise measurements of how much tellurium we can dissolve within it, and that's led us to develop entirely new ways of thinking about chemical loading and chemical compositions. Now, even 1 gram of contamination within 1,000 tons of our chemicals is enough contamination to completely overshadow the neutrinoless double beta decay signal. So we've had to come up with entirely novel chemical purification techniques unlike anything that's ever been required before, and actually built ourselves in ultra-clean environments. This is only doable from the efforts of over 100 scientists and engineers from top institutions around the world, but led here by SOE University. And of course, this is only possible from thousands of liters of coffee. But all this is still not enough to see journalists elevated the game. Because the greatest enemy of all is space itself. Now, as we hurtle through the infinite cosmos, the Earth is being constantly bombarded by highly charged and energetic particles known as cosmic rays. Now, whenever one of these cosmic rays slams into the Earth's atmosphere, it litters us with trillions upon trillions of particles. Thousands of them are passing through your body at this very moment, harmlessly, but the snow plus detector is sensitive enough to see them. Even one of these particles completely overshadows the signal of neutrinos double beta decay. There's only one thing we know that can absorb all the cosmic rays, and that's the Earth's crust, hundreds of meters of it. So this experiment would have to be built deep underground. Lucky for us, there's another group interested in going very deep underground, and we can find them here in northern Canada. The city of Sudbury is this, the Creighton Mine, the deepest nickel mine in the world. So every day, SNOPlus scientists such as myself, with help and support of the miners in the mining community, we go 2 kilometers underground. We hike through the nickel mine until we arrive here. Snow, the deepest and cleanest science facility in the entire world. And it's here, safe from the constant onslaught of cosmic rays, we are building the SNOPlus experiment. The SNOPlus experiment is a combination of physics, chemistry, and engineering, but most importantly, it can only be done through the union of science and industry. We are in the final stages of construction and commissioning and hope to be online soon, and with it, we hope to find neutrino-less double beta decay. If we do, that will be the solution to one of the most basic of all human problems. How do we become beauty? Thank you very much.
Thank you, Ben. That was definitely a great talk. We're going to take some questions before we start the observing for the night. If you have questions, raise your hand. We have a mic over. Please don't start speaking your question before the mic reaches you.
The courtesy of the Nichelle Institute, we have a bunch of these flashlights. These are flashlights, right? And they're tools. They're flashlights with tools for people that ask good questions. I've never seen one before, it's quite exciting.
All right, the Patrick.
Oh, I can shout.
No,
For
that's
the
it.
microphone because we're being screened.
Oh,
So we bring the screen and
Hello. There was a picture where there was a boat.
Yeah,
Is there water in the thing?
that's correct. So,
Sorry.
so that's an excellent question. So in the beginning phases of the SNOPlus experiment, as we're trying to commission, trying to figure out all the problems, we're not filling it immediately with our chemical complex because that would introduce too many different variables. We first started by filling it with water. Currently, we're replacing, at this very moment, we're replacing the water in there with our special chemical complex. As you see, there's a person voting. No, that wasn't me, unfortunately. I was taking a photo. I can find it myself. But that's not only the Guinness Book of World Records deepest voting trip in the world, but also how we go around to make sure there's no impurities or imperfections in the vessel itself. And you go into these cool light things. Oh, there we go. Very good. Any other questions?
So how do you, what if there is a contamination? Because you're going through all of these measures to stop contamination. What happens if something brings something into the snow project?
Well, in the worst case scenario, we would be able to recirculate all the materials inside and push it back through our purification systems. So it would be a several day delay. And based on the severity of the incident, maybe we'd monitor the entire thing to make sure there's no lasting contamination stuck to the vessels or anything. But that all that would mean is that we'd have to recirculate the volume of the chemical complex on the inside and potentially drain a little bit of it. And we do have a process in place to do so. But moreover, we have an extensive QA process developing. Every half hour, all the chemicals are vigorously tested by a team of our chemists on the ground in order to make sure that only the highest purity materials are transferred.
So I'm just curious, how do you know that by putting it underground in Sudbury there that you weren't accidentally also blocking what you're looking for?
So that's because what we're looking for, we're actually putting into the detectors. The tellurium, we're putting inside the detector itself.
Oh, okay, so, okay.
Yeah, we're
that
going to
makes
load
sense.
our chemical complex with about 100 tons of tellurium dissolved within our chemical.
Oh.
Hi there. If you discover or observe the double decay of snow line, is this something that like automatically when you guys are in another
I would say without a shadow of a doubt, if we saw it, it would eventually become a Nobel Prize. Yes. This is what many scientific communities believe to be the most pressing issue in physics today.
How long has it taken to build the big machine making cameras?
So that's a very good question. A lot of the skeleton structure was built over about 10 years for the original snow experiment in the 90s. It's taken us about 5 years to refurbish some of the mold materials and a further 5 years to build the new systems and new chemical purification systems. The final aspects of the construction is actually going to be completed this month. And it's been about a 20-year journey altogether.
So we're going to do one more question. Ben is going to stick around after to ask, to just interact with you. And I'm going to go with... Yes. Apologies, Matt.
I was wondering if this project has ever been attempted before.
Sorry?
Has this project ever been attempted before?
So there are about 3 or 4 simultaneous double beta decay experiments coming online right now. But before this current generation of technology, we did not have nearly enough sensitivity to actually be able to do data like this. So this is the first generation of experiments that are capable of even thinking about seeing this.
All right, so let's thank Ben once again. So before we move on forward, I have been instructed to tell you guys that the beautiful, awesome flashlight / handy tool thing that you got is actually opens up, and there's various options of different screwdrivers in there. So if you're just wondering where the tool set comes in, it's behind the black cap. So because of that, I'm going to keep one. All right, so now it's time for us to actually go up there and observe. We have various different stations over here, as you can see, for you to take in. Where you end up actually depends on the color of the ticket you have. So if you have the red colored ticket, so remember when you came in, you were handed a ticket. If you have a red colored ticket, you're going to come up with me for the main show, the telescope. If you have an orange colored ticket, which apparently is not available, so we had a yellow colored ticket with a blue stripe through it. If you have that, you're going to go to the warm room, which is also the telescope, and go with Drew. Where's Drew? Okay, there's Drew. If you have a green colored ticket, you're going to go onto the roof, where we have various members from the Royal Astronomical Society of Canada set up different telescopes, and we also have a few telescopes from Queen's Observatory that have been set up. You're going to follow Thomas and Liliana. Please. Okay, and finally, if you have a black colored ticket, you're going to get the chance to go to the McDonald Institute Visitor Center, which you're going to follow Matt with. He's also wearing a black shirt, so that makes it easy. Find the person with who has the same color t-shirt. All right, commence!